Okay, so thank you, and thanks for the organizers to invite me here. It's not the first time I'm in Brazil, but it's the first time in Natal, so I check all the cities where there's some science done in Brazil, and there's one or two places left to be checked, but I've been over many places in Brazil, and it's always a pleasure. Okay, so I will speak about light scattering experiments we do in Nice, so the title of my talk is Coherent Light Scattering by Cold Atoms from Anderson to Dicke and back. And I don't know how far I can get back with the time we have. We'll see. I will walk you through some story, and I want to give you the motivation why we do all this. It's a long story. It's over 20 years of research, and we are not done yet. But I hope that in the next couple of years we come to the main goal we try to go to when we move to Nice. So first I want to acknowledge the collaborators. So we have four PIs in Nice, including me. So Mathilde Fouché is working on, all three people are working on cold atom experiments. Everyone has his own cold atom experiment. Mathilde is working on correlations in the cooperative scattering limit. So that's why we want to go beyond the classical limit. I will not speak about this today. William Guérin is in charge of the Subradiance experiments. I will speak about this today. So that's a big chunk of my talk today. Guillaume Labéry has been working on the initial part of this project, which I will discuss, and now he's mainly focused on pattern formation, where we heard a talk this morning by Thorsten Ackermann. And then right now we have two PhD students, Patricia Weiss and Gilles Ferreira, and two postdocs and four PhD students, Anna Cypris, which is working with William on the Subradiance experiments, Marius Gaudesius, Antonin Sisiak, and Pierre Zam on other parts which I will not discuss here today. And then there's a very important list here. I always advertise this, and it takes always a minute of my time, but I think it's very important to have a lot of collaborators for many different reasons, and I particularly stress this for the young people in the room. First, you meet a lot of interesting people. So that's already reason enough to have a lot of collaborators outside of your own group. You can discuss with interesting people with different cultures. It's really worth it. Only this is worth all the suffering we have in our labs. Then second, of course, they have an expertise you do not have. So they help you understanding what you're doing, and you make a big progress and you advance in your science because you have a lot of external collaborators. So internal sterilization is avoided by having a lot of external collaborators. So that's very important for the science part. Then a very productive part is those people also sign the papers you publish. So if you make a mistake, they're all in the trap with you. So they typically don't blame you if you say something in talks. So one thing particular here, so there are many people which are not listed on this collaboration part. These are the people who collaborate on topics I will discuss today. And I put a Brazilian flag, actually not because of this talk, I had this previously, because we have a very strong Brazilian connection, in particular with Romain Bachelard, and so we have a lot of collaborators in Brazil. It's one of my strongest collaborative countries. Anderson is here, there will be Thierry Professor coming on Monday, so I have a lot of collaborators in Brazil. It's a very nice place to have collaborations with, so it's, I really strongly recommend this to all of you. So again, collaboration is very important. Don't try to do things alone in your lab. It's not a good idea. Okay, so this said, coming to science now. So what we do, we have been working with rubidium atoms mainly, and our working horse is this cloud of cold atoms. So our particular expertise is to construct very large cloud of cold atoms. So we trap at least 10 to the 9 atoms and sometimes up to the 10 to the 11 atoms, which allows us to study collective effects. So this is a piece of glass here, a cube of glass 10 by 10 centimeters side, which allows us to trap many, many atoms. And this is very robust. If you want to do this, just come to us or just look at the paper. It's very easy. You do it, you will get the same number of atoms as we have. There's no particular tricks to get 10 to the 10 atoms. It's just large laser beams and a lot of power, so some money to be paid. But that's all it needs. And then once you have this, then you can study different type of physics. So the topic I will discuss today is Dicke and Anderson localization. We'll see this later. But we have heard this morning from Thorsten on pattern formation, plasma physics, so we get also this type of things. In some regimes, the light scattering inside this cloud, light will push atoms. There are forces exerted on atoms, and sometimes this becomes unstable like this. So we don't really understand the dynamics of this. This looks like plasma physics behavior. I don't know if this could be only radiation pressure forces like Coulomb repulsion or attractive forces. That's why I was having a question about elliptical galaxies the other day. If there would be long-range attractive forces in 3D, like 1 over r attractive potential, 1 over r squared attractive forces in 3D, this could be a system where we could simulate gravity in the lab. There's no other system to simulate this. So where are these structures coming from? What are the scales rising from? So these are questions which I think are very important, and we are just at the beginning to understand how this behaves. And then another thing which I have a lot of fun with this, so that's why I put this all over here. We take our expertise in photon detection and all the technology we have in cold atom labs, and we export this to astrophysics colleagues. And so we, in the last years, we have redone intensity correlation on stars, so the Henry Brown Twiss experiments, which have not been done since Henry Brown Twiss in the 70s. And we remeasure stars, and we went to Chile for a big telescope. So the big dream my big dream on this is to find quantum optics in space. And so, okay, this is what you need to do. You need to measure G2 to see if there's quantum optics out of space. So, okay, and then we do random lasing, quantum fluid light, different things, but okay. So I will focus in this talk on only the sub part you can study if you have many atoms and you throw photons at the large cloud of cold atoms. So I will first give a little bit of an overview why we do this, what is the main focus on this. So the quest is endless localization of light. And then I will tell you what we have done so far. So we have partially seen a weak onset of localization, what is called weak localization, many years ago, and more recently subradiance, which is apparently not related to endless localization, but I have to tell you about this too, to show you how we think we can combine these two fields of research to do endless localization of light, of subradiant modes of light, actually. Okay, so this is a kind of an overview and like a summary. So if you only want to take a home message on one single slide, that's the slide you have to remember, please. So the rest, it's getting details, so that's the important slide. So the idea is that we have a large cloud of cold atoms or scatterers. So for our purpose, the atoms are just scatterers. So it could be droplets of water, whatever. So assume that you're all cold atoms, okay? What can happen? I will throw photons on you, and there are different ways. And I want to keep the photon in the room for a long time. Of course, the room has to be big, right? If there's only one atom, it will go away very quickly. But if you have many atoms, okay, maybe this photon will stay in the system for a long time. So what type of features, mechanisms allow the photon to be stored in the sample for a long time? One is shown here. It's just a diffusion equation. So the photon is like a particle. It makes a random walk from one scatterer to the other scatterer, and it will make a Brownian motion, diffusion motion. And the larger the sample, the longer it will take the photon to go to the boundary and escape. So it's something which depends on the size of the system, but it's not depending on the wave nature of the photon. It's a particle type of Brownian motion. Then there are two features mentioned here which depend on the wave nature of the photon. One is called endless localization, and one will be Dicke subradiance. And so the idea is the following: let's say endless localization, we have photons which are shared among a few atoms here. So we share a photon, and the photon is trapped here. It will not escape. So that's one way to trap the photon. And the other atoms do not know that we have a photon trapped here. So it's a spatially localized eigenmode which allows the photon to stay in the system for a long time. But it's spatially confined. And then there's another way, which is what I will describe as a Dicke subradiance, where everybody knows that we have a photon, we share the photon, we just oscillate somehow out of phase, and the photon stays in the system, but we all share the excitation. So it's an extended mode, but it's also a mode which is long-lived. And so there are different mechanisms. So you see there are already 3 different mechanisms here, how to keep a photon in the sample for a long time. And we want to understand these different mechanisms. Are there phase transitions here, how the scaling loss is, and so on. So we want to understand this feature. And the main goal was to observe endless localization of light. But we need to understand the other mechanisms, not to get fooled if you see photons staying in the system for a long time, that it's not radiation trapping or Dicke subradiance. Okay, so endless localization has first been discussed with electrons to understand the transition from a conductor to an insulator, because if you have a localized mode, then the electron cannot make a random walk around the copper wire, and the diffusion will be suppressed, so it will be an insulator. But electrons have strong Coulomb interactions, so people were looking for non-interacting waves. There were matter waves. There were the experiments now with BECs in these other potentials. Kicked rotors have been used. in acoustics, people have been doing experiments with aluminum beads. And so we look for electromagnetic waves, light scattering. And in this community, there have been different approaches by trying to use different samples to make light scattering. So the main samples used were semiconductor powders, white paint, and we now add cold atoms. So that's just different material science, and so that's the context. So we want to look for light localization by using atoms as scatterers. And so there's been, of course, a lot of work. Anders localization has been out for more than 50, 60 years. Of course, there's been a tremendous community working on this. In theory, there's this paper by the Gang of Four, so-called Gang of Four. I will not go into the detail here, but the most important message is that 3D is different from 1 and 2D. 3D, there's a phase transition expected for a kind of strangles disorder, whereas in 1D and 2D, all states are localized. And this depends on the return probability. If you do a random walk only 1D, you will always come back to the initial point, and you will make a self-interference which traps you. In 3D, you might never come back to the point of origin. So that's why 3D is very different. And then there's a scaling law, which I will just come back to this type of figure later on, but we can discuss this, but that's not it's a technique how to describe the existence of a phase transition. Another thing I want to stress is that despite this 60 years old story, there's no exact analytical theory of Anders localization in 3D. There are numerical toy models, but there's no exact theory. And but the beauty of this theory here is that it's assumed to be universal. So it doesn't depend on the detail. If you have semiconductor powder, white paint, cold atom, everything should follow this universal scaling law. And so that's why this paper is so important. Okay, so this is the state of the art. So the main pioneers of this field were Ad Larendyck and Georg Meret, who both did very important experiments, and they thought to have seen Anders localization. And the short story is that in the experiment by Ad Larendyck, absorption was masking the possibility of Anders localization. And in the experiment by Georg Meret, fluorescence was masking the possibility of Anders localization. So there were technical issues in these samples here, which is acknowledged by everyone, including Ad Larendyck and Georg Meret. But they clearly showed us the way to go. Because if you know the trouble of other people, you know what to avoid. So you have to make sure that you don't fall in the same type of problems other people have. So it's even though they didn't see Anders localization, without this we would not be able to formulate our problem as we can do it today. So it's extremely important what they did. So you just have to recognize the work done by the people before you. You're never alone in this type of research. You always follow in steps of your previous research colleagues. Okay, so the status is it has not been observed so far, and at some point in my talk I will show you that there's even a prediction that it might not exist. Okay, so if it doesn't exist, then there's no surprise that they didn't see it, and we'll see if it exists or not. Okay, so what did we do so far? So the first thing is, so we throw photons that are cold atoms. There will be random walk, described by diffusion equation. The diffusion equation is given by the square of the mean free path. How far does the photon go before it changes direction? That's mean free path, which depends on the density, 1 over the density of the scatterers and the scattering cross-section, and there's a time constant associated to how fast this process is happening. And so we do benchmark experiments. If you come with a probe beam on a cloud of cold atoms, if you're on resonance, no photon goes straight through. That's the black line here. So that's the optical depth of the sample. This is described by the Beer-Lambert law, where you can directly extract the mean free path, a very important parameter. But in cold atoms, basically, we don't have absorption. So every photon in is 1 photon out, which means all the photons which are missing in the forward direction, they have to go somewhere. So they are scattered either in the forward direction, diffuse transmission, or in the backward direction, diffuse reflection. And in the forward direction, this can be described by a kind of Ohm's law for photon with this diffusive transfer properties. So we measured this, and this follows this 1 over L's dependence here as a function of optical thickness. So we recovered Ohm's law for photons. All this is just benchmarking, but you need to do this just to make sure that you understand what your experiment is having in the stomach. Then we can also do time result experiments, which with cold atoms is much easier than with white paint or semiconductor powders, because the time scale of cold atoms is given by the by the lifetime of the excited state, which for rubidium atoms is 27 nanoseconds. So today's detectors are fast enough to be able to resolve this. And so what we see here is that if we come with a pulse, we switch off the light, then the photons will be trapped in this room by random walk. And we see that photons leak out a little bit later if there's a large cloud. This is optical depth of the cloud. So if you have more atoms, photons stay in there for a longer time. And from this, you can extract the diffusion coefficient or even the transfer velocity, which comes in here. And the surprise here is that the transfer velocity is many orders of magnitude smaller than the speed of light, which is just explained by the fact that photons, they jump from one atom to the other, and then they stick on one atom for a long time before they go to the next atom. So that's what explains this very slow transfer velocity. And we were even able to make the cold atoms move faster than light in this sample. So just to show you how intriguing this can be. So sometimes photons are slower than cold atoms. So this can happen. But that's nothing to do with interference effects, so nothing to do with localization or even subradiance. But you need to understand this before moving on. Okay, so the interesting thing is if you take into account interference effects, so then this classical diffusion coefficient gets a correction here, which is expected to scale like 1 minus 1 over k L squared, where k is 2 pi over lambda is the wave number, and L this mean free path, how far the photons go. So if the photons travel a long distance before they change direction, this correction is small, but it's a wave correction to the diffusion coefficient. And if k L is of the order of 1, then this might be 0. This means diffusion is frozen, stopped. That's where we expect Anders localization. So one guess of Anders localization is this so-called Joffe-Regel criterion, KL of order of 1, which means that the photon has to scatter in the near field. Every lambda over 2 pi, photon has to change the direction. So this requires a high density of or very efficient scattering sample. Okay, so we did first experiments to see this small correction of the diffusion coefficient, and this is shown here. So we come in with a plane wave here on the disordered medium, and you know that if you look at the function of angle here, you get a speckle field here as a function of direction. If you make a configuration average, then you assume that this speckle field is averaged away, you get a flat line. But in fact, there's a particular combination of paths where you make the interference between the direct path here in full line here and the dotted line here, which inside the sample do exactly the reverse direction. So this is more or less like a Sagnac interferometer, and exactly in the backward direction, this will always interfere constructively, and you get on average, twice more intensity in the backward direction than in the other direction. This means that you do random walk, but you go back a little bit more than in the other direction. This means that all over the diffusion is a little bit reduced. This is the explanation of this reduced diffusion coefficient. So we did this. This has been shown in the 80s with a lot of different samples. You can do this with your hand, with everything you see, basically. So this is done here with a piece of Teflon. This is a speckle field. I would not know from this speckle field if this is a speckle field coming up from many single scattering events or multiple scattering. But now I do a configuration average. I rotate this piece of Teflon. I integrate the data, and what I see is this enhanced backscattering peak here. And this is a proof of interference and multiple scattering. So this is what is called weak localization or precursor of Anders localization or occurring backscattering experiment. So we did this with cold atoms. So we come with laser beam, go on the cloud of cold atoms here, look in the backward direction, put the camera in the focal position of a lens here, and then we see this nice enhancement here. So this is a signature that even if you drive the atoms at resonance, there is an interference effect in multiple scattering, as evidenced by this picture here. And similar experiments have been done by Mark Havey in US, so this is something which is now more or less well understood. Also, comparing to theory, I said there's no exact theory of Anders localization, but there's a diagrammatic approximate approach where you take the direct path and this reciprocal path, which I showed in the other slide by the dotted lines. If you add all this up, and even including the complicated structure of rubidium atoms, our theory colleagues with Dominique Delange, Christian Minatura, they could produce this full line here, which is compared to the dotted points here with experimental data. And this is not the fit. This is just providing them by the shape of the atomic cloud and the number of atoms in density, and this works perfectly. So at this time, many years ago, there was no doubt that this diagrammatic approach is as precise as you can be, right? We did not have a slight doubt that this would lead us to Anders localization, this path of diagrammatic approach. And you will see that now we change our mind, but That's why I pull out this again. It was so exact, so precise that anyone who would put a doubt on this, I would really. Yes. Excuse me? Yeah, so this was in the dilute limit. This, the mean free path was 200 or 300 times wavelengths. So the KL was 200 or 1,000, something, very large. So, and this number KL gives you the width of this cone here. So the larger KL, the smaller the width here. And if you want to go to localization, you need a small KL and a broad cone. Okay, but that was clearly the way to go. And so we need to get the higher density. So people try to do this. Mark Havey, Antoine Brouès has these high density samples. And so far, so they are in the regime where this Schoffer-Regel criterion is fulfilled, but they have not seen localization so far. So, okay, maybe they will see it, but so far they have not seen it. And one important problem is the internal structure of rubidium atoms. I showed you this peak here. There was no scale here. Already you see scales. I told you that we expect a factor of 2. It's sometimes only 1.5, 0.5, 1.2. And this is due to the internal structure of the rubidium atoms, which acts like small magnets. And these magnets break time reversal symmetry, which is very bad for localization. So when we went to a strontium experiment, then we almost recover the full interference effect. So rubidium, we think, is not very good for localization, which means we have to change the atoms, which is costing money and time and not so easy to do in practice. But so far we have stuck to rubidium, but now we'll move on to a new experiment with ytterbium, which is similar to strontium for this purpose. Okay, so we were at that time trying to push to higher densities, and then we stumbled over something different, which was a Dicke type of physics. So I will explain a little bit how we describe now our light scattering with an ab initio model for light scattering. So we have a kind of a microscopic model, not analytical, but microscopic model for our scattering, which we think includes the weak localization correction, the diffusion properties, and endless localization. So we have a model where everything should be included. Wow, that's AT? Or okay, so this is the model. So the idea is that we come on with a plane wave on our atoms, and so dipole J here, for instance, is driven by an external field here with a propagating phase here, and that's the free evolution of this dipole J. But this dipole J is also driven by the light scattered by dipole M, which propagates from M to J with this green function here, which is a simplified version, but it highlights that there's a 1 over R term here, so that's long range. So this propagate green function here makes our problem a long range problem. And once I can solve this, I can compute the light scattered by all these dipoles, and this is what I measure in the experiment. Okay, so this has been used in different limits. So this is an angular profile, emission profile if you come with a laser beam on a cloud of cold atoms. This is numeric. So the blue line is the solution of this coupled dipole model, where I see first a very strong peak in the forward direction. This can be explained by just a homogeneous dielectric piece of atoms. And this acts like a bead of glass, and that's a lens. And so this is like the focal part of a lens. So you don't need disorder, discrete matter. This is a mean field model describes this peak here. Then we have the black points here, which are coming out of an incoherent random walk model, and the blue line of the coupled dipole model behind this. So the coupled dipole model also includes diffusion. So it has diffusion, it has the mean field, and it also has coherent backscattering here. So it has all the features we have known so far included in this set of equations. That's why we like this equation so much for experiment. And this peak here has been recently observed in Junji's group in Jilla. Okay, so this works. This is steady state. Now we go for time dynamics, time result experiments. And for this, we have to think about Dicke type of physics. So Dicke came up with the solution of what happens if you have many two-level systems together, which are more or less sharing the same vacuum modes. And if you start from a fully inverted system, you get a cascade. And I think Susanna will speak about this in detail. We actually, and this has been observed by Feld in the 70s initially. We do not focus on this because we want to focus on linear optics, weak drive limits. So we only focus on the single excitation sector, which is shown here. So we at maximum have one photon in the system. But even in this case, so this is the collective ground state, all atom ground state. And these are all the states where there's one photon in the system. And I can have a symmetric state, and all the other states are the kind of antisymmetric states. and the symmetric state will emit the light much faster than a single atom. So I call this the superradiant state, and all the others are subradiant states. This is n times larger than gamma 0 single atom decay rate for a small sample if the size is smaller than lambda. 5 minutes. And we are working in an experiment where our sample size is much larger than lambda. So I give another key on this, information on this. So how should this scale? And the idea is that it's a little bit like cavity QED. So if you have a cavity with a single mode, if you have n atoms in this cavity, these atoms have to share the mode. So there's a cooperativity which scales like n times the single atom cooperativity. Now in our case, we don't have mirrors, no cavities, we have a large system. The question is, how many optical modes do we have? And we have as many optical modes as I can put lambda squares on the wall of this room. So the number of modes, optical modes, m or n here, is the surface L squared divided by lambda squared. So that's the number of optical modes. And the cooperativity parameter, which we conjecture from this, is the ratio between the number of atoms divided by number of modes. That's what I call B0. And this should be the right scaling parameter for all this cooperativity physics. So it depends on the size of the system. It's not the density. It's not n over KL cubed. So it's not the spatial density. It's not local effect. It's a global effect because we have this long range 1 over r Green function. And we like this very much because this is also the on-resonant optical depth. This is something we can measure in the experiment. So this number here makes theoreticians and experimentalists happy. So that's why we like this number. Okay. Now we want to see this type of effect, so we come on with the pulse, switch off the light, and using this coupled dipole model, we simulate what should happen. Single atom decay is in the dotted line here, and if you have many atoms, then there's a fast decay and a slow decay, and we saw that this, we showed that this slow decay here scales as optical thickness, this B0 parameter, which I introduced on the previous slide. Now we want to do this in the experiment, and again, we need to be sure that we don't mix up random walk, diffusion, localization, and subradiance. So the scaling law for a subradiance should be like B0, which I introduced. Random walk is expected to scale like B squared. There's the 2 here, there's 1 here. And it also depends on the detuning of the laser. If I'm out of resonance, then the optical depth is small for this frequency, and the light will go out very quickly. But for this part here, it does not depend on the detuning. So the scaling for subradiance and radiation trapping is drastically different. And if it were localization, we don't really have the result, but we would expect that it would be an exponential dependence on B of delta. But we don't know, actually. But if I would see this, I would be even more happy than the subradiance. So we need to look at scaling laws to be sure that we can distinguish the different ways of making a photon live in the sample for a long time. So this is the experiment. So what we see here is we switch off the laser, and then most of the light is just going out very quickly, and then at the 10⁻3, 10⁻4 level, you see light staying in the system for a long time. So this is in units of individual atom lifetimes, so it's a few hundred. So these photons here stay in the system for a very, very long time. And we see that if you change the optical thickness here, the slope here changes, so it depends on B0. If you change the tuning, the slope doesn't change. And if you put everything on a single curve, it scales like B0, and it does not scale like B of delta squared. So I think this is a convincing argument that what we see here is described by this coupled dipole model, which we call subradiance. So another thing I want to stress here is the numbers. We have an increase of 2 orders of magnitude of the lifetime compared to single atoms. So it's not a few percent effect, it's a big effect. So we can now use this to work on it and do something different with this, but it's a very important effect. So the thing now is how to make localization of light. And I have 2 minutes, or yes, okay. So we go to a kind of a theory, and just now forget about the experiment, try to think a little bit, go for an effective Hamiltonian, which looks like a little bit an Anderson model of a disordered system. You have hopping from one atom to the other here, and this is the Green function, but that's very important. And for real photons, you don't only have the 1 over r far field, you also have a near field dipole-dipole coupling, which makes things behave very, very differently. And I will show you this here. So coming back to this Gang of 4 paper, where there was an expected phase transition here for the expert, if we do the same type of analysis with our coupled dipole model, we see that if we only take the 1 over r Green function without the near field coupling, we indeed see this crossing here, which corresponds to this crossing here. So there is a phase transition expected for 1 over r, purely 1 over r dipole coupled model. But if you take into account the near field 1 over r cube dipole coupling, then there's no crossing here. So the result is there's no localization for real vectorial light in 3D samples of cold atoms. So basically this means, and this has been done by Sergei Skipetrov in 2014. We got similar results same year. So basically this is very bad news. It should not exist. So end of the story or not. So obviously not, else I would not have another 2 slides or 10 slides. So very soon, if there's a no-go theorem, people come up with routes around things. So you read the small print in the theorem, and then you find ways around. So there are 2 ways around nowadays on the market. One is proposed by Sergei Skipetrov and Igor Sokolov, is apply a very strong magnetic field, and if you tune the laser frequency to one of the Zeeman-shifted lines, then you should see a localization there. And the other approach is something which we came up together with Luca Celardo, is going back to the Anderson model. So we take a dilute system and we add diagonal disorder on this coupled dipole equation, which means that we have to randomly shift every transition frequency of the atoms. So this detuning will be randomly detuned, and then we also see the emergence of localized states here. And so there are 2 different approaches which are on the market, and we are going to try this with a new experiment using ytterbium atoms where this internal structure is solved. And both approaches, this one and this one, are so far based on a study of eigenstates, which we cannot measure, but together with Romain, we have now a prediction how to measure this, and one of the guesses is to look at fluctuations. If you cross a phase transition, the fluctuation of the light coming out will be enhanced, and this is shown here. So we have a prediction how to measure this phase transition in a realistic experimental setting. And with this, I'm over. I thank you for your attention.